Good afternoon, everyone. My name is Mark Dirks, and on behalf of ACRL and Choice, I'd like to welcome you to today's program, Teaching Visual Learners with Data Visualization, Delivering an Active Learning Experience for Engineering Students, which is sponsored by McGraw-Hill Education. Today's discussion is one in a series of sponsored webinars from ACRL and Choice that addresses new ideas, developments, and products of interest to the academic library community. Free to users, these structured 60-minute live presentations provide the opportunity for interactive discussions of important new issues and developments in academic librarianship by librarians, vendors, authors, and other interested stakeholders. Before we get started, I'd like to point out a few features of the webinar software. In the main area of the screen, you can follow along with the presentation materials. Along the right-hand side, you will see a chat panel, which you may use to submit questions or comments. At the end of the presentation, we will take a few minutes to answer your questions, so please feel free to submit them throughout. If you lose audio or would like to change how you are connected to it, look under the chat box on the right-hand side of your screen and click on the phone question mark icon. Please also note that today's program is being recorded, and all registrants will receive follow-up instructions on how to access the archived version. And now, I am very pleased to introduce Dr. Anselm Spoerri. Dr. Spoerri has a PhD from MIT and is a faculty member at the School of Communication and Information at Rutgers University. He has conducted research in the field of information visualization for the last 20 years and teaches students how best to visualize data. A recent co-authored paper about how to visualize what is most controversial in Wikipedia received widespread media attention, including articles in Wired, MIT Technology Review, The Washington Post, and The Economist. Dr. Spoerri leveraged his data visualization expertise to guide the visual display and interactive functionality that are key to AccessEngineering's data viz. At this point, we're ready to get started, so I'll turn the floor over to you, Dr. Spoerri.
Welcome to this webinar. My name is Anselm Spoerri. I'm a faculty member at Rutgers University, and there I also teach in the master's program where we train librarians, and I've had the pleasure of teaching many future librarians in the use of effective data visualization methods. If I were to ask you, how many threes are there? In order to answer that question, you will have to examine each of the letters or the numbers in order to decide, is it a 3 or not? If I had displayed it like this, using color to emphasize or show them in red, then you can instantaneously answer the question, because we have a visual pop-out effect and we can use color to guide the eye. So if you want to be able to make use of such an effect, you have to use color strategically and sparingly. Here we have a square moving in front of a background. They happen to have the same texture, so if the square were to stand still, it would blend perfectly into its surrounding. There's no difference in terms of color between the square and the background. There's no difference in terms of how much light is being reflected back. The only difference is motion. This is a nice example to show that the human visual system is able to process motion information independent of other visual information. It also shows that the visual system cares about and is excellent at detecting sharp changes in a visual feature. That's something it tries to detect very early on when it processes visual information. So when we design visual displays, we have to be mindful that we don't produce visual changes that don't relate or are correlated with the underlying data. So we don't produce visual artifacts. Furthermore, motion, like color, can be a powerful way to guide the eye. So if you have motion in your display, use it again strategically and sparingly. Now, when talking about data visualization, people also sometimes refer to it as information visualization, and also infographics is mentioned in the same context. And if you look at Google Trends, we can see there's been a growing interest in infographics. Yes, there is a steady interest in data visualization that's slowly increasing, and I would not be surprised if it will continue to do so into the future. Now, when it comes to infographics, here's an early example. At the core, we have a bar chart. But the designer decided, rather than just having anonymous bars, to add icons of people in the display to indicate this is about people. So the viewer immediately knows or has a certain context of how to read the display, and it makes it more accessible. There's also different colors being used. Orange is used to indicate that we have a different kind of worker, one that's working in a factory. Then we have also the color blue that's indicating this is the cloth that's being produced. And so we have these two charts combined, and we can see as there's been a shift from people working at home and working more in factories, the production of cloth has dramatically increased over time. If you do a Google search for infographics, an image search, you'll get results like this. And one thing that stands out is the extensive use of color. Strong colors, large fonts in order to highlight key facts. Also the use of icons in order to help the viewer interpret and say, aha, this is what the data is about, rather than some cold numbers. Now, as mentioned with color, there can be too much of a good thing. If you have too many different colors and they sort of negate each other. And as Tufte has been concerned about chart chunk, that especially applies in infographics, that there can be details and decorations in the infographic that actually detracts or is not necessary to communicate the story. Now, like with a good steak, it needs to have a little fat to make it tasty. Yes, you need these visual features to make them accessible to the viewer, but it's a balancing act that you don't want to overdo it. Now, the key thing with an infographic is it's meant to show the essence about the data, the highlights. The designer had to figure out what are the key points about the data and find a visual way to communicate them. And often infographics are static. Now, when we talk about data visualization and interactive data visualizations, we have standard display types, the workhorses, so to speak, that you will find in any tool and in many visual displays, that these types of displays are being used over and over. So we have the bar chart, where the data variable is encoded in terms of the length of a bar, and the human visual system is excellent at being able to compare different bars and be able to tell, are they the same length, or is one twice the size, and so on. So a bar chart really taps into a key visual capability. If you're interested in communicating how things are changing over time, or how a data variable is changing, the line chart is the way to go. The visual system can compute the curvature of the line very easily, or the angle, and immediately detects if there's a sharp change in curvature. Let's say we have a stock chart, and if the stock were to dramatically increase in price or drop in price, the visual system will be able to pinpoint that moment very easily in a line chart. Then we have stacked charts, where we want to show the overall total, but also show how the different components or categories are contributing to the whole. Then we have a pie chart, which is similar about how does the part relate to the whole. And there, as when we were talking about color, we don't want to have too many slices, too many categories or subdivisions that we want to visualize in the pie chart. Because if you have too many slices, too many colors, it's hard for the visual system to decide what to pay attention to. Then we have the bubble chart, where the size of the circle is related to the data variable that's being visualized. Then we have the scatter plot, where we compare two variables, and we are interested whether there is a relationship between those independent variables. And if the dots cluster in a specific fashion, let's say on a line, that's an indication that there could be a linear correlation between those two variables. Or if it's on a smoothly changing line, the visual system is excellent at being able to detect if dots are clustered in an organized fashion. Now, the key to remember is you want to make sure that you pick the right data display to make the patterns in the data visible that you're interested in communicating to the user. So if you want users to be able to compare and make fine judgments about individual data values, then the bar chart is the way to go. If you want to provide an overall sense of how things have changed or are changing, then the line chart is a good choice. If you want to show how variables are related to one another, then the scatter plot is excellent at being able to make that visible. Now, when it comes to contemporary or modern data visualization, there are a few key design principles that I would like to draw your attention to. Now, Remember, it's all about being able to tap into the perceptual capabilities of the viewer so that they can gain insights into the data set. First principle is interactivity, so that the user can interact with a slider and the display gets updated instantaneously. So let's look at an example from the New York Times, a delicate calculator. And as you may recall, in spring of this year, there were the primaries in the US. And if you look at the primaries for the Republican Party, the question was, after March 6, what would happen or how long would it take a candidate to reach the needed number of delegates? And if the candidates had certain percentages of the vote, you could see how quickly they would be able to achieve the number of delegates needed to clinch the nomination. So if, let's say, Rubio had, instead of 28%, gotten 36%, would have been the consequences of that. And immediately you can see, yes, this would have truly changed the nature of the race. So by being able to interact with a slider, the display gets updated, and I can explore a very complex information space by being able to interact with that visualization. Next, we have immediate feedback. That sort of goes hand in hand with interactivity. If you want to support interactivity, you also need to ensure that the display immediately updates. This is also crucial for our motion system, because if there's immediate feedback, then our motion system is able to extract meaningful information from that. Then when we want to explore a large information space, let's say we have 4 different data variables or 10 data variables, there isn't a display that can visualize all 10 data variables at the same time. So we may have multiple displays that show subsets of that data space. And by linking them, we're able to explore and see how one selection in one display plays out in another display. So an example of this is the stacked scatter plot. So here we are exploring the interaction between 4 data variables, and we're looking at pairwise scatter plots. So here we're comparing variable 1 with variable 2, here variable 1 with variable 3. And I notice that here the red dots are tightly clustered. And I'm wondering whether this will be the case also when I compare variable 1 with variable 4. And if I look down here, I can see, yes, it almost has a similar spatial pattern, whereas if I look here, where I'm comparing variable 1 with variable 2, they're much more spread out. So by highlighting certain parts in one display, I can see how it plays out in the other displays. And that allows me then to explore a much larger data space by making use of having linked displays. Next, a principle coined by Ben Schneiderman. We want to provide an overview of the data, so you can see all of it in one shot, and then you can interact with zooming controls and filters in order to focus in on a specific aspect of the data that you're most interested in. And if you found a specific item that you want to know more about, you can mouse over it and you get details on demand. Then we have the principle of dynamic queries. They're related to interactivity and immediate feedback and the ability to filter. So if you look at an example here of parallel coordinates, which is not a standard display, a more specialized display. And here we are able to look at 7 variables at the same time. And without going into how this visualization precisely works, what I want to highlight is, if in terms of the first variable, economy, I'm saying I'm interested only in the data points between 25 and 20. As I interact with the display, immediately it shows me how it plays out in the other data variables. So I'm specifying a query, and as I'm dragging, the display gets immediately updated. The query is being executed, so to speak, and I get instantaneous feedback. So that's what's referred to as a dynamic query. Another principle used in modern data visualization is the concept of focus and context. It doesn't apply to every data set, but imagine you have a very large data space. You want to zoom in right away, but once you're zoomed in, you lose sense of the whole. And you have to back out in order to see, aha, this is how it relates to everything else. Or if you have an image that's high resolution, you're zooming in to be able to look at some pixels in more detail, you want to edit them, and you then have to back out in order to see, how does it connect to the other patterns in the image. So looking at an example in terms of network data, where we have a node link diagram. So here I noticed that the purple dots are clustered, and I wish I could explore them in more detail. And notice as I now move my mouse over, I get a fisheye distortion so that this area of the display is selectively magnified, but I can still see how it relates to the whole structure. If I look at the orange ones down here, I can see, aha, this is the specific relationship between those points, but I still see how it connects to the whole. Further principle is animated transitions, or to animate transitions. And this is all about feeding the motion system and make it easier for people to assimilate the change, rather than showing the beginning state and the end state, and then people having to figure out how did one thing move to the other, or where is it located in the end state. We animate it so the human visual system can track it. So here an example from the New York Times visualizing the US budget. And what we have here is a bubble chart, but now there's more structure in terms of the budget items that are increasing from the previous year are shown in green and they're towards the top, and the ones that are decreasing are shown towards the bottom, and we're using the red color to indicate how much the change is. Now the thing that I want to illustrate here is if you now want to look at different types of spending, and I click here, notice now how this transition is animated, and I can sort of track how the dots are moving to the mandatory part of the display and the discretionary part of the display. If I want to go back to the earlier, I now see how they're being animated again. Yes, there's a lot of little circles to keep track of, but we can sort of get an overall feel, and it becomes much easier for us to make sense, to assimilate what just happened. Finally, the name of the game is to increase information density. We want to pack in as much data as we can, sort of leave no pixel behind. So an example of this is here the tree map, which is a display that was developed in research and is slowly moving into the mainstream. And what are we looking at here? We're looking at a lot of data. We're looking at a hard disk that is hierarchically organized, and the tree map is ideally suited for hierarchical data. Hard disks are organized in folders and they have subfolders and so on. So each folder is a white rectangle and the one within it is a rectangle further in, and the border of the big folders are broader so that they stand out. So I can see here there's one part of the hard disk and then it's further subdivided. The areas are proportional to the size, the file size, or the data variable that's being visualized, and the color to either a categorical data variable or another numerical data variable, and it can change in terms of its shading. So the key thing here is, and this is also a nice example, you're seeing all of it. You're getting a big picture, an overview of the data, of this hierarchical structure, the contents of this hard disk, and then you are able to zoom in as you see fit, maybe interact with some filters in order to emphasize certain parts of the data and then be able to explore it in more detail. Now segueing into talking about how the New York Times is using visualizations, and the reason I want to talk about the New York Times is, from my perspective as a data visualization researcher, it's interesting to see how data visualization is starting or is moving into the mainstream. And the New York Times is using data visualization to enhance its stories, to allow its readers to go deeper into the data, not just look at the facts that have been emphasized by the person writing the articles. They have the choice to explore the data. And the New York Times believes that visualization will be a key component in terms of allowing users to get a better understanding about the story and to make them more engaging. And it's also interesting to see what types of displays the New York Times is using for a general audience. So these are not specialists, these are the general audience that is meant to be able to interact and read those displays. So let's look at a few examples. So here a map, which is another common display type. What's being shown here is what happens to which team people are rooting for in terms of baseball. Using Facebook data, what this display helps answer is, do people root all over the US for the same team, or is who they root for very defined by geography? What we're seeing is, for example, the people who root for the Rangers live in Texas, and where the team is located there, most of the fanhood, so to speak, is the strongest, and then it decays, so to speak. Yes, there's another hot spot over here. If you look at the Giants, the people living in the area of San Francisco root for the Giants, whereas if you look over here, In New England, people are rooting for the Red Sox. So it's spatially defined. And the saturation of the colors gives you a sense how strong they're rooting for this team. And you can see as it moves away, the support decays. The next example I would like to look at from the New York Times is their visualization about the voting habits of Americans. What we have is a scatter plot where we're comparing the percentage voting for the Democrats and the percentage of turnout. So what we have here is all of Americans. A little bit more than 50% voted Democratic, and the turnout was around 60%. Now, was this the same for all the racial groups? And what this visualization shows is there's a difference. The size indicates how many voters are with each of the racial groups. And we can see that the black group votes predominantly Democratic and has a similar turnout as the white group. If you now break it up in terms of education, does that change how the different groups are voting? You can see black voters, regardless of education, vote more for Democrats. Yes, but there's some variation in terms of turnout. If you now bring into the picture whether it's a man or a woman, still a similar pattern for black voters. There's a little bit more of dispersion for Asian or Hispanic voters. If you now bring into the mix 8 different age groups, still predominantly blacks are voting for the Democrats. And if you bring into the picture even which state they were living in, you can see there's a spatial clustering of all the green dots, showing that blacks are predominantly voting for the Democrats. There's quite a bit of dispersion for white voters and the same for Asian and Hispanic voters. Now, the reason this scatter plot works is because there's some structure, there's some spatial clustering taking place. We're looking at a lot of data here, a lot of data variables simultaneously, but because there's some structure, it allows us to infer some useful, meaningful information. And if you compare here now what the voting patterns were for 2004 and how they shifted 2012, we still see that the green dots are clearly spatially clustered. So what we can see here is that this clustering pattern that we've noticed for the green dots is stable across time, and also as we bring in different distinctions that we can make or different variables in terms of state, education, or age, or whether it's man or woman. To summarize, so we have infographics that's showing the data in a distilled form, the highlights, and often does it in a static way. Then if you want to see more of the data, we have interactive data visualization that is very much used by professional and early adopters, but is moving into the mainstream, as we can see by what the New York Times is doing and other newspapers. And then we have visual data analytics, where we're dealing with lots of data, big data. And in order to be able to know which part of the data to focus on, data mining, machine learning techniques are being used to identify the interesting subsets in the data, and then custom displays might be created to be able to explore and better understand the data in a visual way, and there can be a feedback loop. But this is how it all fits together. At the tip of the iceberg, we have infographics, and then as we want to go deeper into the data, we are using interactive data visualization. If you want to explore huge amounts of data, then we will use visual data analytics, where we have a combination between visualization and computational methods, statistical methods, machine learning techniques. Now, segueing over to talking about how can we use data visualization when teaching about material science and engineering. First, I will talk about how students currently learn about material properties, then discuss the process used to create a data visualization tool by McGraw-Hill Education, where I was part of the design team and the data visualization expert to help them guide and develop this tool. And then I will be demonstrating key aspects of the DataVis material properties tool. Today, or currently, students most of the time learn about material properties by looking at a handbook. There's a table of numbers. The rows are different materials, the columns are different material properties, and by learning these numbers and seeing them more and more, they build slowly some intuitive understanding, some conceptual understanding about material properties. Or they may go to MathWeb, look up a specific value, or they may use Google, here the density of steel, but what's missing is how to see it in context. So we want to go beyond the numbers, not just numbers, but promote conceptual understanding. So the students are so busy just finding the values, looking them up, they don't get encouraged to explore why the properties have certain ranges and to start having a higher level understanding of different material classes and so on. If plots are created, often they are static. They do not really promote active learning. And most importantly, engineering is about trade-offs. You have multiple constraints in terms of what a material needs to be in order to, let's say, be used for an airplane. So what faculty need are easy ways to create customized and active learning exercises that use data visualization. So the approach taken for designing this visualization tool was first interviewing educators and students to get a better sense of what their needs are, what they're familiar with in terms of data visualization. Then use an iterative process in terms of developing first the prototype and then the final tool. And most importantly, match the visual displays to the student and faculty needs. So we're building a new data visualization tool. The temptation is great to say, let's build something that is customized, that is novel, that is flashy, but it might have a learning curve that is too steep for the faculty and the students. Instead, we decided let's work with displays that are familiar or easy to learn, and then give them the capability to look at a lot of data variables easily and be able to build it up in a step-by-step fashion and make it more complex or more rich in terms of what they're exploring. Another key design goal was to make it easy to make data ranges and patterns visible that matter when you're thinking about material properties, and to use linked displays to support active learning. So let me now demonstrate the tool. So here we're on the homepage for the Database Material Properties tool. It's part of AccessEngineering. If you have a subscription to AccessEngineering, you will be able to use this tool for free. If you don't, you can test it out. You'll get access to a subset of the data that has been created. A lot of effort went into creating a representative and curated data set that has almost 200 materials and 65 properties. As mentioned, these are representative materials so that the insights that students gain from it are valid, so they're not sort of an artifact of the data that we have included. When coming to the homepage, there are multiple choices. One is students or faculty can compare properties across multiple materials, or they can find a property value for a single material, or if they want, they can look at sample projects where they can see how the tool was used, and if they have an account, they can even make a copy of it and customize it. I'll talk more about that at the end of the presentation. So let me start by comparing properties across multiple materials. So the choice that I have is either to look at one property or to look at two. If I choose two, then a scatter plot will be used and I can see how the two material properties are related with one another. What's their correlation, so to speak. What I want to start out is by looking at one property, and one of the material properties that early on, when people learn about material science, talk about is density. So let me type here density. And what I like about this tool is you don't have to be a perfect speller. As you provided the first few letters, you can see, aha, here we have the physical property density. And let me now walk you through the tool. So what we have here, what's called a dot plot. And the way this display is organized is, notice here are all the metals, and we use a reddish color to indicate these are the metals, and they're spatially organized. They're in this column. Here we have all the polymers, where green is used to indicate, and here the ceramics, here the composites, and here the advanced materials. What we immediately see is not all of these major material classes have the same range of values for density. For example, here I notice there's an outlier, and if I mouse over, I can see it's gold. Gold is very dense. It's a very dense metal. If you look here in terms of ceramics, we have tungsten carbide that is very dense compared to the other ceramics. And if you look here, the polymers are more tightly packed and similar sort of in range in terms of the composite materials, but they don't have the range of values as metals. If you want to expand here, click on the plus sign. We can see the metals when we look at their subcategories. Ferrous, non-ferrous, that the ferrous materials have density values that are between 7,000 and 8,000, whereas there's much more range of values for non-ferrous materials when it comes to density. So the display lets the viewer see easily, instantaneously, what's the range of values, is there some clustering, and start building up some intuitions in terms of this specific material property as it relates. And let me bring back the other major categories or classes of materials and what the differences are between them. Now, if I were to say to you, look, I'm interested, or we are interested in designing an airplane, what would be a suitable material? Now, we would like a material that is not too dense. The higher the density, the heavier it will be. So if I were to say, look, I don't want to consider right now, or I want to de-emphasize materials that have a high density value, I can interact with the slider. And as I'm moving it down, notice how some of the dots change their appearance. They get sort of more, they get reduced in size and they become more faint. They're still there, so I can still consider them, but they're not as prominent in the display. So I can be moving my slider, and I want to have something, set it at 8,500. Here it is almost. Let me type it in precisely, 8,500, and there it is. So the appearance of the dot tells us whether a material is in range or out of range. If it's small, then it means it's out of range. Now, I remember the professor, pretending that I'm a student, mentioned that steels could be a good candidate when we are designing an airplane. So let me see what's the density value for steels. So here I can use the select materials control, and here I can expand and see the hierarchical organization of the materials that are included in this data set. So if I click here on metals, I can see I have my ferrous and non-ferrous materials. And if I click on ferrous, I can see I have iron and steel. So there's 40 steels in the data set. Remember again, these are representative steels that have been included in this data set. So let me first deselect all. So notice what's going to happen when I click deselect all. First, let me draw your attention to the black borders that indicate that the material is selected. I deselect all, and now all of the dots have no black border anymore. If I click on the checkbox for steels, the steels are being highlighted, and I notice I have all these black borders that are quite tightly clustered in space in this metal column. So the steels tend to have density values that are quite similar. If I want to find more about it, I can zoom in further, and I can even drag as I'm doing that, and I can see the steels have values between 7,700 and 8,000. So there's not a lot of variation in terms of the density values when we're talking about steels. Let me zoom back out. Now, I also remember that maybe aluminum alloys could be a choice, or I'm wondering. So where are the aluminum alloys in terms of the metals? I remember they're non-ferrous. Let me click here, and here I see them right away. Aha, there's 27 aluminum alloys that have been included in the data set. And if I click on the checkbox, I can see, here they are. Let me switch to the pointer tool. And they're also spatially quite closely clustered. There's not a lot of variation in terms of density when it comes to aluminum alloys. So in terms of the designing an airplane, maybe aluminum alloys would be the way to go because they have a lower density value. Now, I need a material that is also stiff. And what I want to do in a second is bring in elastic modulus and see how it plays out for steels and aluminum alloys. But before I do that I would also like to see, would titanium be a good choice? So I can go here into my search box, type in titanium. And as I'm typing, I can see the different materials that have these letters. I see there's a metal titanium, and there's also a ceramic material that has titanium in it. The one that I'm interested in is the metal. I select it, and I see, it's sort of in between the aluminum alloys and my steels. To make it further stand out visually, I want to star it so that I remember, this is my titanium. So as mentioned, now I want to bring in elastic modulus to see the stiffness of these different materials. I click on one property, I search for elastic modulus. I have different choices. I want tension, elastic modulus tension. And what will happen is we'll get a display similar to the first one that is placed right next to it. And notice that the appearance of the dots is the same. And if I mouse over here gold, I can see, there is my gold being highlighted in the display. These two displays are linked. So if I make a choice in one, it will play. I can see how it plays out in the other display. So looking here, and let me zoom in a little bit, I can see that, whoops, maybe I did too much zooming. Let me go back out. Also, the steels, let me switch to the pointer tool. I can see that, and I'm guessing because it's occluded, not these dots are being highlighted, that my aluminum alloys tend to have elastic modulus values below 100, so they're not that stiff. And if I look at my steels, since not these are being highlighted, they will have elastic modulus value of around 200. So they're stiffer. They're more dense, but they're more stiff. So if I wanted to actually explore this without having to mouse over in a table view, notice here there is an icon where I can click on that takes me to the tabular representation of the data. You may already see it down here lurking at the page fold. I click here, and now I can look at all the data in a table form. Here's my material. Here are the different properties, the different columns that represent it. To make it easier for me is let me change the display settings, because right now I think all that I want to consider is the metals. I'm not going to worry about ceramics, polymers, as I'm thinking about what would be an appropriate material for an airplane. So I can change my display settings and say I only want to show the selected and in range ones. Here they are. And if I now go to my table view, here I only have now my metals, and I can sort them in terms of density, or I can sort them in terms of elastic modulus. So here I have the lighter materials, so to speak, or the less dense materials, and now I can see, yes, they have an elastic modulus around 70, and as I keep scrolling down, as the density will increase, I can then also see that the elastic modulus is increasing as well. Coming back up. Now, let me clear the search box. So we can see we have right now we're only viewing metals, and these are the metals that we're viewing in terms of ferrous materials. We have the steels. In terms of non-ferrous, we have 27 aluminum alloys and 1 titanium alloy. Now, let me bring all of them back again, just so that we can see them all. When designing an airplane, we also want something that has a good value or property value for fracture toughness. So let me add this into the mix. I'll search for fracture. Here we have fracture toughness. Now this is being added side by side. It's also a linked display, and we can see there's quite a range of values in terms of fracture toughness. So if I highlight this, I can see, and most likely this must be a steel, because it's highlighting values around here, and I know this is where my steels are in terms of density. And if I mouse over here, I can see this is most likely a aluminum alloy, because it's highlighting these dots here that are related to aluminum alloys, which has low fracture toughness. Similarly, if I want lower density, I'll get lower elastic modulus, and I get lower fracture toughness. So it will be a trade-off in terms of what I do. I can see here my titanium is sort of in the middle in terms of the fracture toughness values. Now, when designing, you also have to keep in mind cost. So let me add a cost variable. So let me type in here cost. And I see there's 6 different variables at my disposal. I can look at cost in terms of what it would cost when we have mass production, or we have a project, or we're doing some research. What I'm going to pick is relative cost, which will give me a qualitative measure in the terms of the cost differences between the materials. And what I can see here is, and let me change the display settings again, I only want to show what's selected and in range, that in terms of the metals that I'm considering right now, there's also quite a range of what they cost. I have a material here that is a steel that's quite expensive, that has higher density, higher elastic modulus or stiffness, and since this is occluding it, it must be somewhere down here in terms of its fracture toughness. Whereas if I mouse over here, what I notice is, there I have some cheaper materials. They must be most likely all steels, since they're clustering around 8,000 for density and for around 200 for elastic modulus. And in terms of the fracture toughness, they're not at the bottom of my range, but they're not the top performers. So having these side-by-side displays and having link displays and being able to control what's being shown, being able to control what's selected, being able to control what's in range, I'm able to explore and hone in on what materials could be suitable choices given my design constraints or what I'm trying to build or create. Now, let's say I was a professor, I had just given this demonstration, was the first sort of exploration of materials, and I wish I could save this so that I don't have to start from scratch when I pick it up again when I meet with my students. So the first thing that I want to do is I want to give this project a title. So let's call this Initial Exploration. I might give some high-level description about this project, learning about suitable materials for airplane design, and I have created a first page, and you can notice here there's a plus sign to indicate you can have multiple pages in a project, and let's call this the first pass. If I want to provide some instructions, then I could either give them further information, or this is what I want you to do, or this is what I want you to consider. So right now I'll be very imaginative and just add ABC. And furthermore, what I can do is I can add related content. Let's say I have a set of lectures, or I have a screencast, or there's content in AccessEngineering, articles that I would like my students to read to familiarize themselves, to get more suitable and useful information as they're thinking through the problem of what would be a suitable material for designing an airplane. I can add up to 5 links in this related content area. Now, I want to save this. So I click on the Save button, and if I haven't signed in to my account, let me do that. Submit. And now I need to click again, and I get a confirmation, yes, it has been successfully saved. If I go click here on my projects, I can see all the projects that I've saved. I can easily open them up. If I wanted to, I can do Save As. So this allows others to work with projects that have been created by, let's say, their professor or by their fellow classmates or by another instructor, and then use Save As and then be able to customize it as they see fit. I can share it. So here is my URL that I could send to my students. Say, here is the data visualization project that I would like you to review or use as the starting point for your exercise. I can export the page as a PDF. And if I wanted to be able to cite it, here are some suggestions how I could cite, let's say, a specific value or a display, and so on. Now, I'm doing an introductory material science class. I know that when we're talking about airplane design, it makes no sense to consider polymers, ceramics, and composites in the mix. Let me just constrain it to these 68 materials. That's a rich enough data set for my students to consider. Why don't I exclude all the unselected materials from my data set? They're not gone, but they're not part of the picture, so to speak. So let me click here. Here I get some information how I can change it. If I want to do that, let me click Continue. And now what happens is, if I click here on Show All Included, I don't see any polymers, I don't see any ceramic materials that are being displayed. It's only metals. So this makes it easy for instructors to use this curated representative data set, decide on what subset they want to work with or consider, because it makes more sense given where they are in terms of what they're teaching or what the students are working on. Now, let me save this as well. And if I wanted to change my mind, I can click on the display settings and click on Show All Included and Excluded. And notice now the excluded materials are showing up as little outlines. So I can get a sense, aha, I have excluded from my data set these values. And if I'm interested in materials that are maybe around 6,000, this may be a choice, maybe it's zinc. I can click on it. And if I scroll down in the table, I can see where it is highlighted. Here is my sync material. Here is my include column. I can say, no, I would like to include it as well. Click on this checkbox, click on selected, and now it's part of the mix. And if I wanted then later on, I can or restrict my data set, and now sync would be part of it as well. The last thing that I would like to show you is the pre-created projects. So let me go back to the home page. The moment I click here, since this is a web page, if I close it or go somewhere else, I will lose what I have. Yes, that's okay. I've saved what I care about. Now here on the home page, notice I have sample data visualization projects or data viz projects. So for example, here we have projects created by domain experts, here about basic material properties. Let me open it up. And so what do we have here? We have multiple pages. The first page talks about density. Here is some explanation. If I click on show more, there's some detailed instructions and background information. If I scroll further down, I can see here is the related content. And if I don't want to see this anymore, the text, I can click here on show less. And then the next material property that's being covered is specific gravity. Here we're talking about elastic modules. And then finally here is putting it all together. So if I click on this page, you can see now we have specific gravity, yield strength, and a scatter plot that's comparing yield strength with specific gravity. And remember, these are linked displays. So if I make a selection in here, or when I highlight the material in one of the displays, it will show me the same material in the other displays. So I can really see, there it is, has a very high specific gravity, but in terms of yield strength, it's not that great. And we can also nicely see spatial clustering in terms of here are all the metals, here are the composites. And if we were to use a log scale, then we could see more those dots that were crunched together when we were using a linear scale. And then we can see here there's actually a clustering. And let me zoom in terms on pan at the same time of, if you look in terms of polymers, you can see they're spatially clustered as it relates to yield strength and specific gravity. Now, the key thing here is, if I have an account, I can do save as and use this project as the starting point for, let's say, a lecture that I want to prepare for my class. So I don't have to start from scratch. And then I can decide which of the pages I want to keep, which of the displays I want to keep, what other pages I want to add. So it's very easy to build on what others have created and also to share it with either your colleagues or with your students. Let me go back to the home page of the database tool and let me summarize or highlight some of the things that I've just demonstrated. What we have here with database for material properties is educators get a curated and trustworthy data set. They can compare up to 5 properties side by side. And most importantly, they can create customized learning projects and guide students in a step-by-step fashion. They can also integrate linked content that they already have to augment the learning experience. For students, it's a structured active learning experience. They get to explore visually, they get to create their own visualizations, and it produces active engagement. Thank you so much for your attention, and I will now answer questions.
Thank you, Dr. Spoerri. This is Mark Dirks from ACRL and Choice, and I would like to take a moment to give you a virtual round of applause. Thanks so much for spending time with us today and for sharing some wonderful information. We greatly appreciate your taking the time to do so. As a reminder, we have recorded today's program, so be on the lookout for follow-up emails from ACRL and Choice that will include instructions on how to access the archived version. Thanks again to everyone for joining us. I hope you enjoyed the session and have an excellent day.